Oh, and I'll have to remember if I do share screen to set the sound first. So that's something I need to keep in mind here. So we're back again, and what should be the usual reminder. If you look down below the video, we've got some links and links like Slack, and maybe the Zoom link is in there, and it's got the index for these videos, and it's got the index for original ROS agriculture stuff, and there are some other fun things down there to look at. There's a link out to the YouTube page that has all these, where it stores all these videos too, if you just randomly stumbled on this one. So that being said, last week I was saying I need to work on a project where Bob has a device that puts out an RC pulse to control the speed of his motors. And then he originally had a Sabertooth motor driver board, and it would directly take the RC pulse in and make your motors run. And somewhere along the line, that board quit working, so he bought a new one, and it uses share screen, sound. Oh, so the share sound stayed set when I did this. So anyway, if that should be the right stuff. This is the board. This is the new board that Bob bought, and then he found out it doesn't do the RC. The interface for it is not the RC control stuff, and I think I put that in the chat. Whether I did or not, I can, since I build the chat later on, I will make sure it gets to the chat. So anyway, he bought this board, and here's the interface to it. It uses a forward PWM and a reverse PWM. So the signals here labeled N1 and N2. If you PWM the N1, it's going to turn one direction, or you PWM the N2, it'll turn the other direction. And so it's just a matter, you have to translate. So if you want this to work on an RC, my thought was you just grab a microcontroller, and I was going to use one of the Arduino type, and that this is not real valuable to show you that in a small window. But anyway, if you take an Arduino like that and connect it to your incoming RC, and I found a couple of ways to convert the RC into just a number. So as you move the joystick on your remote control, you get a number in your code to do something with. And then if you convert that number, you can generate the PWM signals to run these motors. So before I move on here, if you dig through here, it'll say the PWM for this motor goes from 0 to 98%. Let me find that statement. Right here, it says PWM controlled duty cycle 0% to 98%. And they don't say it anywhere, but I'm guessing if you go higher than 98%, you're going to burn up your board. So you need to do some way to limit that. And if I were to do a converter on an Arduino, that'd be convenient. Just one line of code you just drop in there and say if the PWM is above this value, which is 98%, then just clip it to 98%. And that way you don't get into the condition where it's higher than that, and you might possibly damage the board. So anyway, that's the new board that Bob bought, and when he saw it wasn't RC control, he said he might just send it back and get the expensive board. And I'm going to continue on with this, and because I don't think it's going to take that much work to get all the stuff to work, and I don't actually have it working yet, but I've been digging around. I got lots of stuff that I found laying around, so I'll try to move forward on that. So then the next one this is the IBT2 board. And see, it says it on the board here. It says IBT2, and their title may or may not say that. It doesn't seem to say it in the title. And again, I'll put a link in for that. And this one works the same way. Let me pull up a picture here. And there's the controls there. You got they call it R and L, which I think stands for right and left. So on the chip, you can see there's two driver chips. So there's a right chip and left chip, I think is where that terminology comes from. But basically, you can consider it forward PWM and reverse PWM. And then right next to it, you've got REN for enable, and LEN for, so you got left enable and right enable, and the right PWM and left PWM. And these other signals there, that RIS and LIS, those are actually outputs that we were discussing that before the meeting. It says those might be current sense outputs, but you can also get some kind of if you get an error, somehow they switch that to diagnostic, and I'd have to read through that to figure out how all that stuff works. And then another option is I have, for instance, here's it's a Cytron single channel 10 amp. Is that what it says up here? Well, here it says 13 amps, even though the part number is MD10. So I think it's a 13 amp board, but it's a single channel. And this one actually has PWM and direction input. That's hard to see, but over here it says DIR, PWM, and ground. So it's got a 3-wire interface. And this one, you create a PWM on the processor, and you got just the direction bit. You can set it high or set it low to make it go forwards and make it go backwards. So that's really the 3 different types of the types of stuff. That's what I have. Now, if we did I skip over this board? Yeah, as I say, this has the say forward PWM and reverse PWM, and otherwise it seems to be the same interface as what's on this board. It's just that this board, they put that limit on, say don't go above 98%. This board does not seem to have that limitation on it. So if you like Al just did, he's got one of the TimerOne processors, and to talk to this board, he defined 2 different output pins, and he's running the Arduino AnalogWrite command to generate a PWM. So he just says do an AnalogWrite on the first pin and it'll turn one direction, or you do the AnalogWrite on the other pin and that will turn it in the other direction. And then it turns out that works because he only needs one board to do that. Well, actually it works because he's using the AnalogWrite. And we were discussing that before the meeting too. And let me show you what I found here. Oh, I probably don't have video up anymore. So I come down. So here's an example of, I was running a power steering motor, the same one that Al is using, and it's one that's bolted on my lawn tractor. If you look up here, here's the lawn tractor, and here's the power steering motor and a bracket that turns the, so it's got a chain drive to turn the steering. So anyway, this was just on my bench. That's a board that's laying right here on the ground that I had this motor bolted onto it. Let me pull it up, and I'm probably getting a lot of ads here. So a couple things to notice. This is the power steering motor here, and here's the actual motor, and this is the gearbox with the shaft sticking out. And I just have a 10-turn potentiometer on the end of that to measure its position. And then down here on this board, I've got a Arduino Nano and a potentiometer to request the position for it. And then back here is that 30 amp, this is a different Cytron board. This is a 30 amp version of that board I just showed you. And the thing is, I've got some code in here that says, read this potentiometer, and then turn it with my fingers, and then turn the motor to match that. And the important thing I wanted to show here was, as the motor's moving, you hear this funny squealing sound that kind of goes, and what that is the noise from the PWM signal that comes into it. Because if you're running the Arduino AnalogWrite command, it has a fixed frequency of approximately 500 hertz, and that's the noise you can hear. You can hear the 500 hertz from the PWM on the motor. Because you'll notice when the motor comes to a stop, it stops squealing, and as soon as I start moving it again, you can hear it making noise. Let me just start over here so you can watch those different things, and you can watch for the fact that when I stop, the noise stops, and when it's moving, you can hear that noise, and that noise will always be there because of the PWM frequency that we're running. And the reason why it stops squealing when the motor comes to a stop is because when the 2 pots are equal, it just does not send out a PWM. So it's not controlling the motor at that point. So that's why it's doing that. So I was telling Al, because he's using the AnalogWrite and he's going to be talking to one of these kind of motors. And I said, well, your motor is going to squeal unless you go to the TimerOne function. He said, oh, what's that? Well, don't, here, let me go one more step here. If you go to the TimerOne function, let's see, back up here. And here's an example of that same motor. So here's the power steering motor. Here's the shaft sticking up, and I've got a chain drive to my steering wheel, and there's just this bracket that I made to hold it. And back here is the 30 amp Cytron driver, and then I've got a proto board with that. It's the same setup I had. It's just now on the vehicle instead of on the table. And the front wheels are laying on the ground, so it's got a fair amount of torque to turn the steering. And when I run this, you'll be able to hear the noise that the chain and the steering wheel's making, and the linkage down here. You might even be able to hear the tires going back and forth, but you'll notice the motor will not squeal. And now that I said all that, I just realized I was watching, and I'm actually pushing the buttons on the board. The board has two push buttons that are like test buttons. You press one, it turns clockwise. Press the other one, it turns counterclockwise. But you don't hear the motor squealing. So apparently the frequency this board is generating, this is all built right into that driver board. Apparently the frequency it's generating is above the level of human hearing. So if you get if definitely if you run 20 kHz, you can't hear it. And you can drop it down, maybe get down to 10 kHz. It'd be starting to be a little bit annoying. And kids and dogs are gonna say, hey, what's that noise? But old people can't hear that noise. So let me back up to maybe these were all done with those test buttons and not the Arduino talking to it. Grab a random one here. And you can watch here to see if I push. Yeah, it looks like I'm just pushing the test buttons. And if I go look up the specs on that board, it might tell me what frequency it is, or I can put a scope on and I'd measure that. Which leads right into the fact I was going to talk about my scope. So anyway, that is the point. If you run your PWM frequency at a high enough frequency, it will not make your motors will not sing when you do that. So here's the TimerOne and Timer3 libraries, and this is documented really well on the PJRC website, which I'll put in the link. And the reason it's documented so well on the TNC website is because they're the ones that wrote this command, I think. And my first thought was, well, if it's written for TNC, it's not going to work on anything else. But you come down here and it says, no, it will work on these libraries used. Somewhere they make the exact statement. It says this is standard Arduino stuff. It should run on anything that's an Arduino type board. And here's several TNCs listed. And here's an Arduino Uno, Arduino Mega. So it does work on these other boards. And I have put this onto an Arduino Nano and was able to get my two hardware PWM pins to work on that. So this is if you're interested in that. If you don't want your you get more resolution on the PWM, and you can set the frequency so you can keep it from squealing. So you can go out and look at this if you want. And somewhere it said also the PWM here, something about, but you can use the library PWM function. And somewhere else I was reading through this stuff when I was reading on the AnalogWrite, and it said PWM as a function, but then they didn't have it documented. So that's something else you can look up and see if there is a PWM function that solves some of the problems. But this one actually, if you go down to the examples, where was it? Well, I don't see it right offhand, but and if you want to run, it turns out you can get two hardware PWMs per timer, and so TimerOne takes the TimerOne and gives you the two channels. If you need more, and your board supports it, you can load up the Timer 3 module and you can get 2 more PWMs. So if you've got a big fancy board, you can get 4 channels. If you've got a crappy board like a Arduino Nano or Uno, those will only do 2 channels of the hardware. And somewhere here, they specifically said 0 to right here. So your resolution goes from 0 to 1023, which I was telling Al that it's 4095, but it's not. It's 1023. So it's double, appears to be double the resolution of the AnalogWrite function. And somewhere they'll give you a limit on the frequencies that it runs at. But I think I've run it at, just come out and said initialize it to 20 kHz, and then just use this command here, the pin and the duty. Say go to pin 9 and give me a duty cycle of 50% or 75% or whatever, and that all works great. So that's so again, if you want to know more about this, check out this website, and maybe somebody should look up this PWM function and see what that is. That it could be that's another valid alternative, but for right now, I don't know. So let's see. We talked about this board. This is the board that Al has right now that he's playing with, and I've got a couple of them. Here's one right here, and I've got wires on it. I took the heatsink off the back of mine, and I'm not going to go into that a lot right now. It's just that if you read through the comments on this board down at the bottom, somebody says, "Oh, by the way, they're claiming that these holes through the board should be filled with solder in order to transfer heat better through the board." And I'm not sure that's really true, but his whole point was that's a manufacturing defect, that those should have been so full of solder. And then the other thing is, they say when they ship it, these pins here get bent because they just throw it in a bag, and then Amazon throws it around. And that was their 2 major complaints. Except then they went on to say, one guy got 2 boards that don't work right out of the box. And here he was checking it with an ohm meter, and he's got 5 ohms between the 2 motor leads. And he tracked it down to the fact that he claims that it's because I don't have that picture, I don't think. He claims that when this heatsink is bolted on, there's no insulation between all these open vias and the back of the heatsink. And the reasoning is usually that people will say, well, I've got a heatsink that's anodized aluminum, and the anodizing insulates it to some degree. But he's claiming when he looked at the back of the heatsink, he could see holes in it. So something they tightened it down against here had broken through the anodizing and caused a problem. So at one point, somebody said, well, put Kapton tape across these. And then somebody said put like a thermal pad across these, because this is where the heat comes through from the back. So you put a thermal pad, then put the heatsink back on, and they're claiming that's going to solve all your problems. Somebody's saying actually fill the holes with solder, but I haven't seen anywhere that anybody else say you need to do that. And because when you create a via like that or any pad, you drill a hole through the board and then you plate it so it's got copper. The barrels, what we call the barrel of the via, is made out of copper, and that may transfer enough heat. But my thought is, I'm currently just going to take the heatsink off, and if my board gets hot, then I'll put it back on and decide what to do about it. And older boards like this, or not older boards, but other boards, this happens to be one of those Cytron boards, and it's just got bare MOSFETs on there, and they claim you can run 10 amps continuous through this board. And it's just the modern MOSFETs are much better, and they don't dissipate as much heat. And I've got other, well, we can go back to this. So on this board, they do have this is probably has 8 MOSFETs under this board. Then they got a heatsink bolted across the top of it. This is the one we're just looking at. Here's I got the heatsink bolted to the back of the board. And then here's what the Cytron boards look like, where it's just got bare MOSFETs there. And then I thought I had the other one pulled up, but I don't seem to. No, I don't have it. But anyway, the 30 amp Cytron boards, again, just have, I think it's got twice as many MOSFETs. And again, they don't have heat sinks on. So I'm going to start off on mine and try running it without a heat sink and just see how hot these chips here get without a heatsink on the back. And if I have problems, I'll put a heatsink back on. So that's kind of the options that everybody's playing with motor drivers right now. And that's that I want to try. I'll try my Cytron boards, and I'll try my these boards, these like the one on the screen here. Try one of these boards and work out the ways, the difference of the pins to get these things to drive them. And I came up with various schemes to do that. So I'll present more on that next week. And then, as I say, that's when I ran into the thing about if you run the AnalogWrite as opposed to TimerOne, you can either make your motors squeal and play music or keep them nice and quiet. Was there anything else on that? Let's leave that for this week, and then I'll move on to something else here. So the other thing I was doing was no more fun pictures there. Okay, so let me kill this. Stop sharing. Move this over here. So the other thing is, as I thought part of my documentation process, I've got this cute little oscilloscope. It's an O1. I think it's a DS70. DS7102, and it's 100 megahertz and 1 gigasample per second as a dual channel scope. So it just, in general, it's a modern scope, and you can see it's fairly thin. I was trying to think, how could I use this to create a video? I thought, well, one thing I can do is just like this, put it up in front of the camera, and you can watch the screen while it's running. Or I thought if I just lay it on the table flat, it's only about 2.5 inches thick. If I just lay it on the table, and this is, I wasn't really prepared to do this, but I'll do it this way again, where I'll say, here's my circuitry on the table. And I'll try to do this fairly slowly here. Oh, there's my robot. Let's see if I just mount a camera over the table so I can see the oscilloscope and my stuff down here. So if I say, oh, if I turn this knob, then we could watch the oscilloscope and see what it's doing. So that might work. And otherwise, it came with some software you load it up, and it's got a USB cable. You're supposed to be able to get at least the waveforms to show up on a computer. So you get the waveforms. It might even tell you what the switches and everything are set at. And that's a new enough and fancy enough. It's got cursors on the screen. So if you've got a say a waveform on the screen, you can set a cursor at the rising edge and a cursor at the falling edge. And down here it says, oh, that's 29.3 K hertz, and it's this time between those. So it's handy to have that. So if we were going to say, look at an RC signal, we could put it on the screen and say, well, across the whole screen here, that's about a 60 hertz of the entire RC the frame, because on RC they make a frame where it comes out of your transmitter, and there's a pulse here, a pulse here, a pulse here, and they stack up 8 pulses, and then there's a gap to tell it to reset. And you can pull it on the scope and say, well, that's about 60 hertz. So we put our cursor on there, and it'll say, oh, that's a time of 16.67 milliseconds. And if you take the reciprocal of that, that says that's 60 hertz. So you can get all the stuff right off the scope, and then you can zoom in on one of the pulses. And if I'm just generating single pulse, there'll only be one there to start with. But you can watch that. It'll vary between 1 millisecond to 2 milliseconds as you move your joystick back and forth. Or if I had this box hooked up as a reference, and as you turn this knob back and forth, what's coming out of the pins here will the pulse width will range from 1 millisecond to 2 milliseconds. So I want to present something, say, here's how you generate. If you don't have a box like this, you can take a random Arduino and a potentiometer and generate your own pulses. Or what was the other thing I was going to say? Generate your own pulses. I forgot where that was going. So anyway, I was going to say, here's how you can generate a single pulse if you don't have this little box, or you can use a little box, and then go through and say, here's how you take an Arduino, and here's how you measure the incoming RC pulse width. And then say, okay, now if we want to drive this type of motor driver board, we need these few lines of code. And to drive the other type of board, we need this other few lines of code. And then at one point, when we're talking about the PWM channels, the hardware versus software, if you don't have enough hardware PWM pins, you can create one PWM per board and then create a direction bit. And that's exactly what this board wants anyway. it's got those 3 pins that you feed into it. And then you, by putting a couple logic gates between that and say one of these kind of boards, then you can get the, you can generate that forward PWM or reverse PWM and make that work. So that's just, various things to think about and various ways to get around these things. So hopefully, I was planning to have that done by this week and I didn't. So maybe I can figure out how to get my scope hooked up so we can watch signals and find some motors to drive, and maybe we can go on from there. And I think looking through my list here, let's see, am I still sharing? No, I'm not sharing. Okay, that's good. Put this over here. So I think that I think I didn't make notes before I started this, so I think that basically covers what I was trying to do and some philosophy behind what I'm trying to do. So I guess I'll turn it over to Al then.
Well, thanks for going through that. Those oscilloscopes always look like Harry Potter magic to me. I'm like, it's not a skill or knowledge that I have, so that's always cool to see. And that whining noise, yes, I definitely have a Cytron motor controller, and that whining noise is very annoying when testing, when the tractor is running, that drowns out that whining noise. But
Well, it turns out that's not specific to the Cytron board. Any motor driver you put on is going to do that. It all comes back to your PWM, how you what frequency you generate your PWM at. So that IBT2 board is also going to make. I noticed we couldn't hear it squealing because that motor was really loud that you had. So, but it may get quieter if you run it at a PWM that you can't hear.
Yeah, setting the noise aside for a second, the notion of having more resolution is definitely appealing too, because given up, if I can deduce that will help improve steering accuracy and control, that's absolutely something that would be interesting, so, or useful and beneficial. So I'll definitely go down that timer route. And based on that PJRC documentation, I'm lucky that my teensy pins 3 and 4 are open at the moment. So that's definitely a good thing. On my side, I've made a couple of posts to Slack. Let me share my screen. One of those posts was a video of me testing speaking of motor controllers, the JRK motor controller, which is for the linear actuator. I'm not going to play this whole thing. I'm just going to try to get to a couple of screenshots. This is what's in the view at the moment is part of my electronics board on the tractor and the various mounted components. This is where the JRK motor controller is, and the teensy feeding it. This, as a reminder, is controlling my transmission. Motor controller for. If I can just get. So this is the back side. Here's the linear actuator connected to the hydrostatic transmission that's connecting these two wheels. I was just trying to see if this physical connection was going to work for me. In the sort of the short story is I think it's going to. I think I'm getting a good inch in reverse and a good inch going forward, and this linear actuator is able to provide enough oomph to pull against that hydrostatic transmission control arm. So, and I was a little bit nervous about that because I don't think that motor controller is like their beefy one. So I think it's only designed to put out 2 amps. So that's all good news that I won't be able to confirm until I get it out in the yard and actually move it around and see if I can get speed in the control. It is working. This is a shot that probably was worth figuring out neutral. This switch here is the reverse sensing switch to confirm the transmission is in reverse mode. And neutral is just basically just off of that, meaning this control rod is where it is at the moment. So figuring out neutral, figuring out full reverse, figuring out full forward, and what's the right signal to send to the linear actuator is. I'll say I have version 0 of those numbers at the moment, and see this being forward. You see the gap between the switch and the control rod larger. We'll know when I get back into the yard testing whether or not I've got the control. I think I do. The other post that I made is related to steering motor controller, which Jeff talked, provided a lot of good information about the IBT2, which is what I've got hooked up here. Power coming out of the fuse block into that, and then the teensy bean over here with two of the lines consumed, and then a ground. Actually, quite by accident, disconnected that ground, and it still ran. So there must be some sharing of grounds between, even though the USB is connected to the RPi and the RPi is connected to the battery. Anyway, I was surprised that ground was enough, but it worked. So anyway, in that video was just a little bit of progress of using the potentiometer on my radio control to talk to this NRF radio, and then feeding that data into the teensy and driving the IBT controller based on the potentiometer on the radio control.
Well, you got that picture up right there. Your thing shows that you have R enable, left enable, or R enable and L enable, and VCC tied together. Are you actually putting 5 volts into that, or you just have those 3 tied together?
I have those 3 tied together, and this VCC is outputting 5 volts. So this VCC is driving these 2 pins high.
Maybe you got a different version board than I do, because the one I have in the schematics don't say that board's generating 5 volts anywhere. They make the comment that, oh, you can use the internal 5 volt supply, but I when I look at the board, I don't see anything generating 5 volts on that. So I thought you had to put that in. And depending whose diagram you look at, they are connecting that VCC to their Arduino type board to supply it with 5 volts.
Yeah, I was going to do that too, and then I realized there's actually voltage on that VCC. I'm like, hey, this isn't input, this is output. Well, anyway, that's what I guessed. Beats the heck out of me where it's coming from.
Well, if it acts weird or chatters or anything, you might want to, give it an actual 5 volts into that and see what it does.
Yeah, good point. And then in the video, I just ran through, as Jeff mentioned, a little bit of the code, and where he noticed that I was using the AnalogWrite, which I'll try now to switch over to that TimerOne functionality that PJR wrote. So that is additionally, I'm using this tool Easy EDA to sort of lay stuff out for my wiring, and I also used it for the radio control PCB, but At this stage, I'm just trying to use it as a documentation tool here. So the next thing I need to do is set up the wiring for my potentiometer, which tracks actual steer angle, and feed that into software on the Teensy, which would, use a PID and figure out when I'm in auto mode, the steering. So just the physical connectivity of this multi-turn potentiometer is where I'm at. At the same time, I was going to go through the process of taking a small proto board, putting a 3-wire connector on that for the potentiometer, but at the same time have wire connectors for the inductive sensors that I'll ultimately get to as well. So you do a little bit of software, then you do a little electronics, then you do a little hardware. I'm back at sort of figuring out how things are going to fit on the board, and what I'm intending to do is physically up here next to the RPI where I have a LED lamp at the moment, scooting the LED lamp away and putting up another small proto board similar to this, and doing some of my connections up there. So that's the next step for this wire. Is, I think, it's like a 14 gauge wire. 10 gauge.
I think we lost your audio. I can hear you again now.
I'm here. Can you hear me?
Yeah, I can hear you now.
So anyway, my next step is to get the physical connection for my steer angle sensor and do some more testing with feeding that in and rewriting my software to go back to PID control for the steer angle sensor. So making a little progress, inch by inch. That's it for me.
I was trying to think if Bob had mentioned anything that we should mention, but I can't think of what it was.
Well, you definitely gave him feedback on his motor controller that you were trying to test out and show him how to do that. That was cool.
I threw out some ideas there. I'm not sure it's enough to actually do anything. So maybe if I get something actually running here, it'll make more sense.
I think I'm all set.
Okay. End. Stop.